Part 2, the Hubble distance. For every distance we consider at a time different than now, there are two different but related versions of that distance. We will use the proper distance, d sub p, the actual distance across space at the time of interest. For two galaxies extremely distant from one another, both galaxies are flowing with the Hubble flow of the expanding universe, and any peculiar motion due to nearby gravitational attraction is generally less significant. The proper distance between the two galaxies increases with time, proportional to the scale factor A of t, as the universe expands. That is fairly easy to visualize. Take a galaxy that is 1,000 megaparsecs from us today, scale factor 1. When the scale factor reaches 2, about 11 billion years from now, the proper distance between that galaxy and us will be 2,000 megaparsecs. There is also the co-moving distance. We will not use the co-moving distance in this video, but it is necessary to derive some results. If you are reading some article and you see co-moving distance, you will need to learn the distinction between co-moving and proper distances, which we will not cover. We will call the time derivative of the proper distance due to expansion the recession velocity v sub p. This is the recession velocity of a given galaxy at a given proper distance from us. It turns out that this equals the Hubble parameter, h of t, times the proper distance at that time. In the main course, we learned how the Hubble parameter, h, varies with the energy densities of the components of the universe. Those energy densities vary with the scale factor, A, of t, which varies with time. In this supplement, we will only handle a universe that continues to expand forever, not contract. We will restrict kappa in the curvature term on the right to be 0, such that the curvature term is 0, a flat universe. The remaining three terms are non-negative, and the scale factor A of t will increase monotonically with time. We will restrict W for the dark energy term to be W equals -1. This makes the exponent in the dark energy term 0 and the constant dark energy density, and this universe ends in a big chill, not a big rip. Under these restrictions, the Hubble parameter will decrease monotonically with the scale factor and with time. For constant, non-zero dark energy density, the Hubble parameter will tend to a fixed positive value characteristic of the exponential expansion at large scale factor in the future. So the recession velocity is the product of the Hubble parameter, which decreases with time, and the proper distance to some galaxy, which increases with time. So we need to determine whether the recession velocity increases or decreases with time. We will call the time derivative of the recession velocity due to expansion the recession acceleration, A sub p. It turns out that this equals the proper distance times an acceleration term that we covered in the main course. In the main course, we saw that radiation dominates the early universe and the expanding universe decelerates. At a particular scale factor, matter dominates and the expanding universe continues to decelerate. Then at a higher particular scale factor, dark energy begins to dominate and the expanding universe accelerates. For the case we are interested in, the expansion will continue to accelerate forever. $6.14 billion years ago, when our universe was 7.63 billion years old, at scale factor 0.61 and redshift z 0.64, the expansion of our universe stopped decelerating and began to accelerate. This means that the recession velocity, always positive, between some distant galaxy and us was decelerating with time from the Big Bang till the inflection time, was increasing after the inflection time, and will continue to increase with time and scale factor forever, though slowly. We will come back to this inflection time shortly. The Hubble time is 1 over the Hubble parameter, so the Hubble time will increase monotonically with the scale factor and with time. Multiplying the Hubble time by the speed of light, we get the Hubble distance at a given time. We will call this capital D sub capital H, though I don't think there is a standard notation. The Hubble distance increases monotonically with time for the conditions we're assuming. The blue curve is the Hubble distance in megaparsecs versus time in billions of years from 0 to 50 billion years. At any given time, the Hubble distance for that time is the proper distance from our location at which a very distant galaxy would be receding from us due to the expansion of the universe at exactly the speed of light at that time. Just a reminder that we have assumed a big chill future, not a big rip. Surrounding us, or any point in the expanding universe, is an imaginary expanding Hubble sphere, containing all the galaxies that are receding from us at less than the speed of light at that time. The Hubble sphere is the locus of points in space that are receding from us presently at exactly the speed of light. The Hubble sphere lies within our observable universe and is expanding in time as the universe expands, for a flat universe and constant dark energy density. The Hubble surface is receding away from us. The Hubble distance now is 4430 megaparsecs. This is the dark blue square on the blue curve. The Hubble distance increases with time for the restrictions we have set. For constant dark energy density, the Hubble distance will tend to a fixed positive value at infinite scale factor and time. This Hubble distance will tend to 5340 megaparsecs during exponential expansion if dark energy density is constant and the current cosmological parameters are correct. The Hubble distance equaled 3080 megaparsecs at the inflection time of 7.63 billion years, 6.14 billion years ago. This is the red dot on the blue curve. Take a galaxy located at the Hubble distance at the inflection time. The dashed red line shows the galaxy's proper distance from us at later times, always beyond the Hubble surface. Receding from us at faster than the speed of light due to accelerated expansion. Take a galaxy located at the Hubble distance at a time before the inflection time. Its recession speed from us is the speed of light at that time, but will soon thereafter be less than the speed of light because expansion is decelerating. Take a galaxy located at the Hubble distance at a time after the inflection time. Its recession speed from us is the speed of light at that time, but will soon thereafter be greater than the speed of light because expansion is accelerating. For a distant galaxy closer to us than the Hubble distance at the inflection time, 3080 megaparsecs, so closer to us than that, there is a larger scale factor at which that galaxy crosses beyond the Hubble surface, overtakes the Hubble surface. The green curve is 500 megaparsecs from us at the inflection time. 500 is less than 3080. And it will cross the Hubble distance around 46 billion years after the Big Bang. The purple dot-dashed curve is the Hubble distance divided by the scale factor for that time. For any given time, a point on this curve tells you how far from us now a galaxy must be to be at the Hubble distance at the given time. You might have to give this some thought. Galaxies closer to us today than today's Hubble distance will pass beyond the Hubble surface in the future exponential expansion. We will look at this another way shortly. Distant galaxies are moving away from us, but the Hubble distance is also increasing with time. We need some math to understand how this works. After cosmic inflation, early in the universe, expansion was strongly decelerating, dominated by radiation. The deceleration term, Q, was 1. The Hubble surface and the cosmic particle horizon coincided, and both receded at twice the speed of light. This is the narrow spike at the upper left of the graph. After 300 million years, matter slowed the Hubble surface recession speed down to 1.5 times the speed of light, where it remained for a billion years before the dark energy further slowed it. In our exponentially expanding Big Chill future, Q will approach -1, the Hubble surface will approach a constant maximum size, and its recession speed will approach 0. The situation would be different for the Big Rip case. Q was 0 at the inflection time 6.14 billion years ago, when expansion changed from decelerating to accelerating. The Hubble distance was 3080 megaparsecs at that time. The Hubble surface recession speed was exactly the speed of light. This is the red dot on the curve. Before the inflection time, expansion was decelerating, galaxies' recession speeds were decreasing, and the Hubble surface was receding faster than the speed of light. Galaxies that were receding from us slightly faster than the speed of light would be overtaken by the Hubble surface receding faster than the speed of light. The galaxy would subsequently be receding from us slower than the speed of light. The galaxy would enter the Hubble sphere from beyond. After the inflection time, expansion was accelerating. Galaxies' recession speeds were and are increasing. Galaxies receding from us at an accelerating rate will overtake the Hubble surface, receding slower than the speed of light. Galaxies will subsequently be receding from us faster than the speed of light. These galaxies will exit the Hubble sphere permanently. Let's consider a galaxy that is exactly the Hubble distance away from us now, 4430 megaparsecs. The scale factor now is 1. The recession velocity is the speed of light. The scale factor will be 2 in 11.1 billion years. That galaxy will be 8860 megaparsecs from us then. The Hubble distance will be 5190 megaparsecs then, and the galaxy will be beyond the Hubble distance for that time and forever after, receding faster than the speed of light, while the Hubble distance recedes at less than the speed of light. A galaxy that crosses the Hubble distance at scale factor 2 is only 2595 megaparsecs from us now. So all the galaxies further from us than 2595 megaparsecs today will be beyond the Hubble surface in the future after scale factor 2. Distant galaxies cross beyond the Hubble distance and remain beyond the Hubble distance due to accelerating expansion. Then galaxies that were a little less distant cross over. More and more galaxies cross over as time passes. We assumed constant dark energy density with a big chill end to the universe. If dark energy density increases with scale factor, W less than -1, with a big rip end to the universe, then the Hubble distance decreases once dark energy dominates expansion. As the scale factor approaches infinity, at the finite end to the universe, the Hubble distance tends to 0. This completes the section on the Hubble distance.